Thanks. Well, it's a while since I've given a talk, but I was asked very kindly by Bristol to do this, so I'm happy to be here. Really, this is kind of a summary of what we've done in collaboration with MIT and Bristol in the last few years, and an overview of where we might have to go from a cryogenics perspective in the next 5 to 10 years, although I'm not claiming I know the answer to all of that, but I'll try. So the long-term vision for a quantum computer, well, there's three main options. Firstly, if you can remove the need for cryogenics, great, but I don't think anyone thinks that's possible at the moment. If you do, keep it quiet, because we don't want you to do that. Secondly, working at higher temperatures, which by higher temperature still mean greater than 4K. Slightly unhappy face there for two reasons. One, it's quite hard, particularly for things like the photon detectors that you guys are using a lot. To get them working at good efficiencies at higher temperatures is proving hard. And again, that's bad news for ICE as a company, because we specialize in sub-4K cryogenics. So the third is what we're really looking at, which is simplifying and scaling the cryogenics so that you guys can use it at the powers, the temperatures you need it to work at, but without having to worry about it, without having to be experts in cryogenics like you used to have to be in the lab days to run a wet dilution fridge. If anyone's ever run one of those, you'll know it's a pain in the neck and pretty much a full-time job, and takes over from actually doing your science. So we're going to try and simplify and scale. So just for the non-cryogenics people in the room, this is the area that we're working in between 4 and 0 Kelvin. Typically these will split out into these regimes, which you can achieve with just helium-4 down to about 1.5K. If you use helium-3, you can get down to 300 milli-K, and if you're just mixing the two together, you can get towards 10 milli-K. Now, for a lot of the solid-state quantum computing work that's been going on, it's all been done in the dilution fridge range. Over the last 10 to 15 years, dry dilution fridges have become much more accessible, much more user-friendly, and there's hundreds of them out there now. Probably getting on close to 500-600 systems out there in the world, I would think, for quantum computing applications. We were approached about 3 years ago by MIT to make a system working in this regime, which is below 1.5K, where you typically work with helium-4, but above the 300 milli-K for helium-3. Which is a bit awkward, to be honest, but our engineers like a challenge, so we said we'd try. Before I just go into that in more detail, the argument that always comes up in cryogenics these days is wet versus dry. For the last 10, 15 years, everything's moved towards what we call dry cryogenics, which means you don't have your liquid nitrogen, your liquid helium tanks coming to fill up your system. So a few pros and cons there of wet versus dry, but the big cons for dry systems are basically you're limited by cooling power. These cold heads that you can buy commercially have been used in MRI systems for many years now, are limited to about 1.5 watts at 4.2 Kelvin. It's pretty difficult to get any bigger than that without, spending a huge amount of money. And you also get mechanical vibrations which are induced by these cold heads, which you don't necessarily get with liquid cryogens. But the benefits of the dry systems, they're less expensive to run, they are infinite, whereas liquid helium is a finite resource. As soon as we let it go into the atmosphere, it's gone. It's a lot safer and a lot easier to use, and there's a huge amount more space available for you to put your experiment and all of your wiring and so forth into the cryostat. So where are we at the moment? Well, as of now, as of just a couple of weeks ago when we installed the system at Bristol, we've managed to achieve cooling powers of 340 milliwatts at 1.0 Kelvin, which is a good start. 5 years ago, we were talking about 50 milliwatts at 1.6 Kelvin for a helium-4 system. We've been told that really what the guys think they might need to get a quantum computer working is more like 5 watts at 1.1, 1.0 Kelvin. So obviously that's 10, 15 times higher than what we're achieving at the moment. On dilution fridges, we're maxing out at about 1 milliwatts at 100 milli-K. Even though I work in cryogenics, I don't really have a clear idea of where people think they might end up needing to be for solid-state quantum computing I know that D-Wave are working on a machine that's around about this cooling power at the moment, so that's a good indicator, but I don't want to go into that argument. Wiring, typically 10 to 50 coax on a helium-4 system, and up to a maximum around 100 coax cables going into a dry dilution fridge. And in the future, from what I've gathered here at Bristol mainly, is that you might only need hundreds of coaxes on a helium-4 1 Kelvin system for photonic quantum computing, whereas solid state with dilution fridges, you may need thousands of coaxes, which in itself is a huge problem, and may mean that scaling of photonics is a way better option in the long run. Cooling powers that we're getting now, this is just a quick graph to show you for every 8 kilowatts of input power that we're putting in from electrical power, this is the cooling power that we're getting. Obviously it's dropping off incredibly quickly from 4K down to where we are with about 0.2 watts at 1K, and so on down. So it obviously becomes more and more challenging the lower in temperature you go. And why are we using this cryogenics? Well, the main reason is for getting your single photon detectors down below 1.1K where their efficiency is good enough. But you need to combine that with the cooling of the optical switches that are used in the photonic circuits, which are outputting around 5 milliwatts of power to operate. And unfortunately, you need lots of those at the moment to get any of these photonic circuits really working. We also then need to remove the heat load from any coaxes that are coming down from the top of the cryostat and any fiber optics going into the system. And something that's coming around more and more is embedding cold electronics onto the 50K and 4K stages, which is a collaboration that we might be looking at again with Bristol and hopefully with Keysight, which the next speaker, Nikki's going to, is from Keysight. She's not necessarily talking about that, but there's a lot of work going into that as well. So as I said, 5 years ago, even as it was 5 years ago, no one was interested in these high cooling power 1K systems. We had just very basic 1K pot with a very small pumping line, and you just flood your helium-4, your liquid in there, and you'd pump on it, and you'd get your sample down to 1.3 Kelvin, do some basic experiments. You'd have a small little pump that's only about this big, and that would be enough to do the job. And then, of course, the MIT and the Bristol guys came along saying, well, actually, we want a watt of cooling power at 1.0 Kelvin. And we stupidly said, oh, okay, we'll have a look. And, well, as I said, we're about 340 milliwatts now at the moment. So we're not at 1 watt yet, but this is the system that's been installed in Bristol just 6 weeks ago with the 340 milliwatts of cooling power. You can see it has a 1K pot on it, the size of a dinner plate. Huge amount of expensive things like silver heat exchangers in there. It's got by far the biggest pumping line I've ever seen in my life, attached to about a ton's worth of pump, just to pump on the helium-4 hard enough to get the pressure down low enough to maintain the 1.0 Kelvin with the 340 milliwatts of heat load. It's a very interesting system. As you guessed, this pump's quite big, it's quite noisy, so I'm sure we'll be getting a few comments and complaints from neighbouring labs about the operation of this cryostat, but this really is a world beater at the moment. It's just been installed in Bristol, and nothing else is close to it in terms of cooling power and temperature performance. So we're pretty proud to have that set up here, and we're really looking forward to seeing the results from these guys. This is sort of the inside of the system in a little more detail. I won't go into this too much, there's a bit more on the next slides about this. But what you can see, we've had to use a combination of 2 mechanical cold heads, a single stage which is providing quite a lot of cooling power, around 50 watts at 20K, and then a single 1.5 watt cold head at 4K. And we use this in combination because we're having to sorry, just go back to this one. So what we're having to do is we store some high purity helium gas in here, and we feed that into the system. We then have to liquefy that room temperature gas as quickly as we can to feed it into the 1K pot. Because at the same time we're feeding that in, we're pumping it out with this huge great pump, which is trying to pump it out as quickly as it can. And then it feeds out of the back of the pump back into here, and the whole thing is just running continuously on loop. what we had to do a huge amount of work on was on the heat exchange, on the flow paths, to try and get that room temperature helium-4 gas back into the system as quickly as possible. So whereas previously you would just feed this directly in via a single heat exchanger at the bottom of the 4K cold head, we're feeding it into a first heat exchanger here on the single stage high cooling power cold head. It then goes into a cassette which is embedded within the 1K pot pumping line itself to provide, because of the cold gas you've got coming out of the 1K pot, you're getting a lot of free cooling from that. Feeding it into the next cold head, which is at 4.2K, but we're trying to get it as close to 4K as we can before it goes in there. Once we've liquefied it at the 4K stage, we're feeding it back into the pumping line for a second time at a colder part of the pumping line, so it's as close to 1K as we can get it before it goes into the 1K pot. So this is minimizing the heat loads coming, this pretty big heat load from the warm helium-4 coming back into the 1K pot, so we're really pushing that very hard. And all of that has allowed us to get to this sort of 340 milliwatts cooling power, which is a great step forward, but obviously the scientists here always want more. The exit line for the helium, as you can see, is shown here, so we're pumped, the large 1-ton pump is connected to the top of the pumping line here. The helium-4 is coming out of the 1K pot and it's pre-cooling this heat exchanger and then the second heat exchanger here before it goes out into the room temperature pump and back into the dump. So that's just a very brief overview of what we've done. So just in summary, really managing your experimental heat loads anytime you go below 4 Kelvin is pretty critical. That graph that I showed you of the cooling power dropping off exponentially is pretty damning. This is what we're up to now. We're hoping to be up to around 1 watt within 2 years, which hopefully will be a step towards what the photonics guys need here to do some higher power computing. And just a caveat, if 5 watts at 1K is really what is required, which is what I've been told by the scientists here, then you might be looking at 200 kilowatts of power just to run the cryostat. And you might be looking at around £250,000 a year just to run your cryostat. So, quantum computer's never going to be cheap, but it's definitely not going to be cheap. That's just like right. And obviously then your wiring in cold electronics is critical. So, hopefully that gave you a good overview, but thanks for your time, and if anyone's got any questions, then fire away.
Just wondering, in terms of vibration, you mentioned that the dry pump, there's a drawback of using dry pumps is the vibration. Have you come across some mitigation scheme or how much vibration do you measure?
Well, there's 2 main sources of vibration on the system. One is the mechanical cold heads, which are producing around 20 microns of vibration mechanically, and that's pretty much linked directly in. What you can see is what we've done here is we've put a set of bellows in to isolate the cold head from the cryostat, which brings the vibration down to sort of the 4 to 5 micron level. And then the pump itself obviously is producing a huge amount of vibration, which is transmitted down this pumping line, but that's a little easier to isolate. You can just put that pumping line in concrete blocks or through a wall or something to really hold it rigidly and remove those vibrations. So that's not too bad. We installed it here and there was a vibration specification of sub 10 microns for Bristol, which is what they thought would be the limit where it starts to affect their experiment. And we're within that at the moment. For dilution fridges, the requirement seems to be heading more towards sub 100 nanometer levels of vibration for their experiments, which again is a lot harder to do when you're using these mechanical cold heads of the pumps.
Any other questions? So, could it be simpler from a power consumption point of view to, maybe not.
To use a wet system?
Yeah.
Yeah, it's not an easy answer, but
So I had a question. So
Yeah.
when you design these systems, how do you model the heat transfer? What do you use to simulate the whole?
well, we do a few calculations, and we got involved with the pump companies to model the flow.
Are
the
you
pressure.
finite element calculations of the whole
No, we're not. We're not big enough companies to do that, unfortunately. So it's basically good old-fashioned engineering experience, a lot of it. And
So do you build scale models? Like how do you design a first system in the world?
well, I skipped a few stages. Obviously, we didn't jump from that very basic one to this system that we've been through a lot in the last 15 years of ICE. We've been steadily progressing on increased cooling power on dry systems, and it's sort of culminated in this. So it's not really been a jump like that. It has been a steady build over the last 10 years, really.
Any other questions? If not, let's